Okay, everybody, here we are with the wave behaviors practice problems. Number one, it says, while playing with a spring with your friends, like a slinky, you send some pulses down as shown. So here we send this positive pulse down to an open end, and we want to know how it comes back reflected. Well, in that case, since it's open end reflection, it will come back as the same pulse. It will not be inverted. It'll just be going the other way back to you. If we look at this one here, positive pulse heading towards a fixed end, well, that's going to reflect back to you, but it will be inverted and a negative pulse. Number two, this is to explain constructive and destructive interference and what it looks like before, during, and after. During constructive interference, we create a wave that is much larger in amplitude. Actually, it would be twice the amplitude of these waves. And after that, those waves will just keep passing through each other and going their same directions again. So if this were, let's see, if this were pulse A and this were pulse B before, then B would keep moving to the left and A would keep moving to the right afterwards. So waves simply pass through each other. For destructive interference, here we have a positive A pulse and a negative B pulse, for example. Well, positive and negative pulse will make zero, so a completely destructive interference with zero amplitude. Of course, after they destructively interfere, pulse A will keep moving to the right, and pulse B will keep moving to the left because waves are just energy passing through each other. All right, now we're on to some standing wave problems with number 3. It says, sketch a diagram of a fourth order standing wave, label the characteristics. So here's fourth order. We'll just kind of loop it along like this. There's 1, 2, 3, 4 antinodes that we have here. So here's one antinode, 2, 3, and 4 antinodes. The other one here, so there would be 1, 2, 3, 4, 5 nodes. And again, these bigger areas here in between are called the antinodes. Okay, we want to see how are they produced, right? So antinodes, that is by constructive interference because they're making bigger waves. That's the largest part of amplitude of the wave. The nodes are points of zero amplitude, so those are destructive interference. So here we have waves that are continuously interfering, and we don't see their left to right motion, but we see the result of them interfering. Okay, 4 and 5. This gets us some more problems with standing waves. So this says first order standing wave. So let's draw a first order standing wave here. And 2 nodes. It says they're standing 3 meters apart. So this is 3 meters. And they want to know what the wavelength is. So if you recall from previous stuff here that we've done, the wavelength of a standing wave is just node to node distance times 2. So if it's 3 meters from node to node, that's 3 meters. So that means our wavelength of our standing wave is going to be 3 meters times 2 in this case, or 6 meters for that first order standing wave. All right, let's look at number 5. It says on a spring, students produce 6 order standing waves. We'll do that again. So we need 6 antinodes. That's going to be like 3, 4, 5, 6 or so. Let's see if these all connect out. This is not my best work here, people. All right, so there's 6 order. Yeah, I've done better. All right, maybe you'll do better, right? It's going to be 2, 3, 4, 5, 6, 7 nodes. And again, the black dots are the nodes. 0 interference, or 0 amplitude for destructive interference. The large areas in between are the antinodes, and there's 6 of them. hence a sixth order standing wave. The other thing it said was, let's see, they're sitting 6 meters apart, so this distance is 6 meters. So yeah, if you have a slinky, give it a shot, right? Be careful though, because you have to have a pretty high frequency there. So they also say, vibrating 12 times per second. So frequency then looks like it's going to be 12 hertz, because it just says that in the problem. Right up here, 12 times per second. What's the wavelength? Well, again, wavelength of a standing wave is node to node times 2. So if we find node to node distance, which would be maybe here, well, if this is 6 meters across, and one of those sections would be 1 meter, right? It's that easy, everybody. So let's mark that on there, 1 meter, because this would be a meter here as well, a meter, a meter, a meter, a meter for 6 meters total distance. So one section is going to be a meter. So that means our wavelength is going to be 1 meter times 2, or 2 meters. Lastly, what's the velocity of the waves? Wave equation is frequency times wavelength, so that's going to be 12 hertz times 2 meters, or 24 meters per second. Thanks, everybody.